All right, for video 2, we're going to talk about the trapezoidal approximation method and also something called over and under estimations. Before we get into trapezoidal approximation method, let's talk about a trapezoid. Now, I know by definition, trapezoids have to have parallel sides, and I drew a special one where we have a 90-degree angle here. And the reason why we're doing this is when we create a graph, we're going to have endpoints, dots, one here, and there might be more, right? It might go like this, and this might be our function. Well, between every pair of dots, we can create a trapezoid. And what do we have? We have the width, which is officially the height in the formula, so I'll share that with you in a second. And then this is going to be considered base 1 and base 2. Base 1 and base 2 are considered the sides that are parallel. So what is the area formula for a trapezoid? Well, going back to geometry, it's base 1 plus base 2 times the height. And you definitely have to have this memorized. So if you don't, write it down somewhere, base 1, base 2, notice that's going to be the outputs on our graph. Okay? So if I was to draw a graph, let's say I had a function like this, here's one trapezoid. Now notice the height is really the same thing as the width, and that's what we found in the midpoint example on the last video, was what's the distance between the x values. All right, so what if I wanted to find the second trapezoid? Well, where is that? Here's the one base, and if I connect this, I end up with, you can think of this as base 1, base 2, and then the width between the x's is kind of considered the height. And then it would keep going, right? Here's another trapezoid. Here's another trapezoid. And here's another trapezoid. So we're just going to find the area of each one and add them up. All right, so here's a quick example. Don't write this, I just want you to watch it. So we know that the integral, right, this symbol, the integral symbol with something dx, is actually equal to the accumulation model. Think of that word accumulation as sum, right? It adds up the area underneath the curves. So an integral is the accumulation model. It is the sum or the total area between a function and the x-axis. The next example kind of has us determine the accumulation of snow over a specific time period. So I'm going to pause this and make a quick graph just so we can visually get this. All right, so I made a really quick graph. Notice our x values is time, and then the rate. Now that's important to note that this is the rate of snowfall in inches. I should have put inches per hour. Right, so I'm going to basically look at and find the area underneath this curve, and we're going to use trapezoids to do this. We're going to use the trapezoidal approximation method to estimate the total amount of snow received between 7 a.m. and 8:30 p.m. So what I want to do then is I want to kind of think of, all right, well, how can I think of this? We have to be very careful with how we set this up. So first, all I did was just graph at 7 a.m. Here's my rate, 1.2. At 10 p.m., 0.8. 3 was 1.5. 8:30 was 1.3. Now this is okay because we don't really need a graph to do this. We could do the same thing we did up here, right? The same thing. I could draw a trapezoid here, but I wanted you to just see what this looks like. So if I go from the first data point up, that's base 1. If I go across and then down, there's base 2, and the height is the distance between 7 a.m. and 10 a.m. Well, what is that? That's 3 hours, right? So how many hours have passed? 10 minus 7 is 3. So you can think of that as your height, and I want to find the area for this shape. Well, what is that? I'm going to do it over here. That's 1/2 base 1. Now, what is base 1? Base 1 is the output. So right here, this is base 1 at 1.2 plus what's the output at 10 a.m.? That's base 2. That's 0.8. And then I have to times by the height. And what is that height? Well, the height is the distance or the width between 7 and 10, and that was 3. All right, and that would be the area of the first triangle, trapezoid. Now we do have to be careful because I should have wrote this from the start. Well, what are we doing? We're going from 7 a.m. to 8:30 p.m. and my function, which it didn't give us one, so I'm just going to say S of t. That's snowfall per time. Is just going to be the sum, and it should be approximate, of each one of these three trapezoids. So now I'll use a different color, and now I'm going to draw the next trapezoid between 10 a.m. and 3 p.m. So I'm going to go up, over, and down, and there's my trapezoid. Now notice, the green base 2 now becomes base 1 for the next trapezoid, and then I've got base 2 here. Well, what are their outputs? You can find that in the table. This base 2 in green now becomes base 1, right? And maybe I should draw this differently so it actually looks like a trapezoid. And it would peak up on this side because 1.5 is higher than 0.8. But there's base 1. That's this point. Here's base 2 at 1.5. And then the width is the distance between 10 a.m. and 3 p.m. So how many hours passed? And that width would be 5 because there's 5 hours from 10 a.m. to 3 p.m. So 1/2 base 1, well, what is base 1? It's 0.8 plus base 2, which was 1.5. And you can see that here, went up 0.8, up 1.5, times the height or width, which is 5. All right, and then the last one is the trapezoid between 3 p.m. and 8:30. So how many hours passed from 3 to 8:30? That's 5.5. And then base 1 now was the purple base 2. So that's where you have to be careful. Sometimes on these trapezoids, when you use some of these twice. So there's base 1, and here's base 2. So what is it? It's 1/2 base 1, which is 1.5, plus 1.3 times the height, or the width between 3:30 or 3 o'clock and 8:30, which is 5.5. And then we're going to find the area of each one and add it up. All right, so once you find the area of each trapezoid here, you've got 3 of them, add them up, and remember what this is. This is the accumulation of snowfall. So we took the rates, and we found the area under the curve of the rates, and that gave us the total amount of snowfall in inches. Now notice this is an approximation method. That's why we use the roughly equal to symbol. All right, let's try another one. This is kind of what you'll see in delta math. And my goal is, can we do this without creating a graph? If you need to visually, go ahead and create your graph. But what I'm hoping is we can find the total sum of f of x from 3 to 17 using the trapezoidal sum. And then they say 5 subintervals, so I need 5 trapezoids. Now notice, if I just look between, here's 1, 2, 3, 4, 5. So we have them in between. I'm going to try to color coordinate this. And keep in mind, what is the area formula for a trapezoid? And where does base 1, base 2, where are they present? Those are the y values. Right, so these are the bases. And then where's the height? The height is the distance between the x values. And I use that term height pretty loosely. So let's try it. Well, notice this base 1 goes up to 24 and this base 2 goes to 21. So it's going to be taller on the left, a little bit shorter on the right. And then, so it would be a 24 by 21 trapezoid. And then the width or the height is the distance between the x's, which is 3. So what would I do? I would do 1/2 base 1 plus base 2 times the height. The width is from 3 to 6. Now, the next one, And I think it's important to color coordinate this. The next one is going to go from 22 to 19, so it's going to be taller on this side. And I'm kind of exaggerating these, but here's what we got. Well, now base 1 for the blue trapezoid is 21, and base 2 is 19. What is the width? Well, the distance between 6 and 7 is 1. So 1/2 base 1 plus base 2 times the height, which is 1, and that'll give me the area for that trapezoid. All right, so pause. I'm going to pause this and let you guys finish the rest, and then I'll show you my answer. All right, so if you need to, go ahead and pause the video and just double check your answers to mine. But I found the area of each trapezoid, and the total sum, the total area underneath this curve, if I was to graph it, would add up to an estimate of 225.5 total units using the trapezoidal sum approximation. All right, so we've done rectangles with the left end, right end, and the midpoint, and now we did one with trapezoids. But what about some of the ones that are a little more unique? Okay, so now notice, what if my function is x, the square root of x? Well, we're going to approach this the same way we did before, and notice they say use trapezoids. What I would do is we're going to create a table, right? Because if they don't give me a table, you want to create one. So we know x, we know y. We could call this f of x, same thing. But I'm going to go from 0 to 4, and I want 4 equal subintervals. Because that word equal, I'm technically finding the width of each one, which was 4 minus 0 divided by 4, which each width is 1. So that's really nice and friendly. I'm going to go up by 1 each time. And you don't really need a calculator for 0, right? Plug in 0, plug in 1, square root of 2, I'm just going to leave these, and then the square root of 4 is 2. So I'm not going to grab a calculator because it's non-calculator based, and our answer might not be a full, complete answer then, right? I mean, it's going to include radicals, which is completely fine. Well, now it's the exact same thing. I need to find the trapezoids between each one of these. I'm going to go up. And now this is interesting because it's a 0, but even if you accidentally drew it like this, okay, you would put a 0 for base 1 and a 1 for base 2, and you would still do 1/2 0 plus 1 times the height, which is the distance between. Now notice, all of the distance between each interval, or the height, is 1 because of the word equal. So I know that this is going to be a 1, which makes this really quick. You hopefully don't even need to draw these pictures in. But I'm going to draw them in just to kind of help you out. Right? So here's the new base 1. Here's base 2 for the red ones. So 1/2 base 1 plus base 2. And then my height is technically 1. Now, people are going to always ask, do I have to write it if it's a 1? Technically, no. But I recommend writing it just because you want to make sure you don't ever miss that. So what about the next one? Here's my trapezoid. We now have base 1, base 2. So 1/2 base 1 plus base 2 times the height, which is 1. And then the last trapezoid. I'm going to go up, base 1, base 2. The height is still 1. Now, here's my advice. If this was a free response question on an AP test, that is an acceptable answer. You can stop right there. They don't give you any extra credit or extra points for algebraically solving. I'll show you how far I get with solving. I'll pause it and work through it. Okay, just to double check, if you want to go through how far could you get without a calculator. Well, you can multiply these together. 1 times 1 times a half is a half. And then here, I can't add a real term and a radical, so I'm going to leave it, but I can distribute the 1/2, and times them by 1 doesn't change it. And then here, I've got 1 square root of 2 and 1 square root of 2, which is 2 square roots of 2, but then I'll times it by a half, so I get square root of 2. And then here I distributed the 1/2 again. And then I realized I have a, ooh, you know what? Actually, hold on. This is wrong. I'm going to change it quick. Okay, there, I fixed it. I had a square root of 2 over 2 plus just a square root of 2, and I accidentally added them. I needed to have a same denominator here. So then I get 3 square roots of 2 over 2, and that's about as far as you can go. You could do some more creative algebra, but at some point it just isn't worth it. So I would stop right there. Don't get too wrapped up in the algebra solving. Like I said, you can officially stop here if it's a free response question. You don't need to break it down to that. Now you would if it's multiple choice though. All right, so what about this concept here? As an example, we want to find the area between, now notice, find the area between the graph and the x-axis. That's another thing of saying find the integral when x is 0 to 4. So I want to go from 0 to 4 of y, right? And I'm going to call this f of x just because that's probably more familiar. So instead of y, I'll call it f of x. All right, now we're going to do this using geometry first. So let's look at a graph. What would it look like if I told you to find the area from 0 to 4? Now notice they didn't tell me intervals, right? So we're kind of getting to more of an exact answer. So if I gave you this shape right here, and you drew a nice perfect graph, now we know that because it's linear, right? So actually instead of f of x, what I should have wrote is the equation right here. 1 plus x over 2, right? So I want to find the exact area under this curve. Well, I can do that pretty quickly. This is just a trapezoid. It's got a base 1 of 1. It's got a base here. Now notice the output. This distance is 3. And then what's the width? From 0 to 4, it's 4. So I would do 1/2 base 1 plus base 2 times the height. And 4 times 4 is 16. 16 cut in half is 8. Okay, now we're getting to this a little bit, so I'm just kind of feeding the idea. How does this work with antiderivatives? This is a very interesting concept because we just saw that, and by the way, if I write this as x divided by 2, I'm going to take an antiderivative of this. I'm going to call it at 1/2 times x. That's a lot friendlier. So here's one of the big connections. I need to find whose derivative gave me this, right? I want to take the antiderivative. So whose derivative gives me 1? It's just x. Now, technically, remember there's a 1 here already. What if I add 1 to that? So this will be x squared. But now wait a minute, there was a 1/2 already there. And if I put a 2 up top, I have to multiply by the reciprocal of that 1/2. Okay? Now, we are going to, this is kind of sloppy, so let me rewrite it. 1/2 times 1/2 is 1/4. And then what happens now to these endpoints? Well, we're going to get into this a lot sooner, but when I take the antiderivative, now a lot of people are saying, what happens to the plus c, right? This is something when you have ends, the plus c is already taken care of. So if there's a number here, if there's a limit for 0 and a limit at 4, then you don't have to worry about the plus c. Okay? Well, what does this mean? Well, now I'm going to take 4, I'm going to plug it into both of these spots. So 4 plus 1/4 times 4 squared. And then what we do is we're going to actually subtract the value at 0. Now what happens if I plug in 0 right here? Right? 0 plus 1/4 times 0 squared. Well, that whole thing is 0, so that's not going to change it. And 4 squared is 16. 16 times 4, or I mean 16 times 1/4 is 4. 4 plus 4 is 8. Notice I get the exact same answer graphically as I do using the antiderivative, so I don't even need a graph. That's a big connection that's coming up really soon. All right, the next couple slides, I just want to quick kind of talk about, don't write these, but let's think about what do we know about something called an over versus underestimation. So let's take this example. If f is increasing on the intervals from a to b, determine whether the approximation will be an overestimation or an underestimation for each RAM. So what if I ask you to do the left RAM on this graph? Notice it's increasing. This function is increasing. So if I take the left endpoints and I draw a rectangle, here's my left. Remember, left is that corner. And then I go to the next one. And then I go to the next one. And we don't use that last endpoint on the left. Well, notice, is this area representative of the area under the curve? Is it an overestimate or an underestimate? Well, there's extra spaces here, here, and here that we didn't account for. So if your function is increasing, then the left RAM will always be an underestimation. Well, what about the right? Right? Because isn't the right then using the one on the right-hand side? So if we do the right, we ignore the first one, and I want to create a rectangle using the right-hand side. So see how that dots on the right-hand side? And then here, and here. Now notice, the area under this curve would cover everything and more. So if your function is increasing, then the right approximation method is going to give you an overestimate. So it's all dealing with if the function's increasing or decreasing. Now, what if it's switched? Right? What if the function is decreasing? Okay, so let me look at this one. Here's a left RAM. So if we do the left RAM, we want the left-hand side to start first. Go down. So first off, when we say decreasing, see how the function is decreasing? And then if I go from the left side here, we ignore the last one on the left hand. Well, notice the area under this blue curve and the x-axis is an overestimation because this extra piece is being counted. So this would be the overestimate. And what if I did the right-hand approximation method? Right? So in that case, we ignore the first one here and we deal with the right-hand side. And you can see here, there's a lot of extra space that wasn't accounted for. So this would be the underestimation. Okay. So it's all if the function is increasing or decreasing, it tells us something about the left and the right RAM. Okay, this one I definitely don't want you to even write, but there's something special. And these were two problems that I had from an earlier class a couple of years ago. So what if I did the LRAM on this example, and I got 14.875. And then I did the right RAM, and I got 11.875. Well, first off, overall, even though that this small part is an underestimation, look at all the overestimations here. So the left RAM would be an overestimation for this whole interval. The right one would be mostly an underestimation. You can see all the extra stuff that's not accounted for. But how does the trapezoidal one relate to the left and the right RAM? Well, here is the actual trapezoidal one. And notice I got 13.375. Well, 13.375 is really kind of right in the middle of those. So what if I took the left RAM and right RAM and I added them up? And you can check this right now with the calculator. If I add those up and divide by 2, if I find the average, that gives me exactly the trapezoidal method. So here's a little hint. If you do the left and you do the right, take the average, and you don't have to do any of the extra work because you automatically know what the trapezoidal should be. All right. Since we're talking about trapezoidals, when is a trapezoidal an over or an underestimation? Well, this one deals with concavity, not increasing or decreasing. You got to be careful with this one. And my advice is if you come across a problem like this, draw a picture. If it says it's concave down, draw a function that's concave down. This is concave down and increasing. And look at what would happen if I drew trapezoids here. See how those trapezoids are going to fall underneath? So if it's concave down and it's trapezoid, this would be an underestimate. But what if it was concave up? Well, when I draw this little space is going to be just over that curved line. And you can see I've got my 3 trapezoids, and all 3 of them would be overestimations. So if it's concave up, it's going to be an overestimate using the trapezoidal approximation method. If it's concave down, it'll be an underestimation. All right, and then finally, I think this slide was a slide off. Should have been earlier, but the trapezoidal approximation method is just the average of the left RAM and the right RAM. Okay, so here's what we got. Your homework tonight is we watched 2 different videos. It is the first page is all antiderivatives. And then on the second page, it's one problem, but I want you to use these directions. Find the LRAM, RRAM, and trapezoidal approximation method, and they give a graph. Use the entire graph. So you're really just using the graph from number 3 and ignoring all the directions, and you're going to find the intervals from 1 to 5. So you would basically set up a table, and I want equal intervals. So on your table, you're going to go 1, 2, 3, 4, 5. All right, so that's all I got. I will not have any office hours today either because I have to watch my daughter all day. So I'll see you all on Thursday and Friday. You do have a quiz on Wednesday, so just be aware of that. Quiz on Wednesday, it's going to cover antiderivatives, LRAM, RRAM, the midpoint, and trapezoidal. Good luck. Have a good day.